In this module, we're focusing on programming languages within the context of software development security. The emphasis is on identifying and applying the right security controls throughout the development process. This involves exploring the secure practices and careful considerations necessary when selecting, deploying, and maintaining programming languages. By the end of this course segment, you'll gain the foundational knowledge required to build applications that are both robust and secure. Understanding these practices is vital for enhancing the security posture of your software in today's evolving threat landscape. In this session, we are focusing on the integration of security throughout the software development lifecycle, or SDLC, emphasizing its importance in reducing vulnerabilities across the development process. When selecting a programming language, it's important to consider those that offer strong security features to ensure the robustness of your applications. Additionally, developers should adhere to secure coding practices. This includes principles that build resilience against potential attacks. Another foundational element is threat modeling, which involves identifying and mitigating potential threats early in the development stage, thereby enhancing the security posture of your software right from the start. These components collectively contribute to a more secure software development environment. In this slide, we are focusing on secure coding principles that are essential for programming languages. To start with, input validation is a fundamental aspect. It's vital to properly validate and sanitize all user inputs to prevent common injection attacks, which are a significant threat vector. Next, we have memory management. Properly managing memory allocation and deallocation is critical to avoiding vulnerabilities such as buffer overflows, which can compromise application security. Lastly, we address error handling. Implementing robust error handling techniques ensures that sensitive information is not leaked through error messages, further securing your application. These principles are key to developing secure software applications. On this slide, we explore the importance of threat modeling when selecting a programming language. First, we identify potential threats and vulnerabilities inherent to various programming languages. Understanding these threats helps us comprehend the security challenges each language might present. Next, we evaluate available mitigations by looking into the security features and controls of each language, which assist in addressing these identified threats. Finally, it's about selecting the optimal language. This involves choosing a language that provides a balanced mix of functionality and security according to your project's needs. Making a well-informed choice here ensures that you're setting a strong foundation for secure coding practices going forward. When evaluating the security features of programming languages, there are several key areas to consider that can have a significant impact on the safety and reliability of your software. Firstly, type safety is an essential aspect. Languages with strong type systems can help prevent common vulnerabilities, such as buffer overflows, by catching errors at compile time rather than runtime. Another critical area is memory management. Automated memory management, like garbage collection, can significantly reduce the risks associated with memory-related flaws, such as memory leaks or buffer overread and overwrite, which are common in languages without this feature. Exception handling is also a crucial feature. Robust exception handling can prevent issues like information leakage and denial of service attacks by ensuring that unexpected conditions are managed gracefully without exposing sensitive data or causing the system to crash. Lastly, the availability of security libraries is a vital consideration. Languages that offer secure cryptographic, authentication, and other security-focused libraries allow developers to integrate robust security measures into their applications, reducing the burden of implementing security measures from scratch and lowering the likelihood of vulnerabilities in your software. In this slide, we're focusing on the secure deployment and configuration of programming languages. To ensure security, it's important to deploy programming languages with secure default settings and hardened configurations. This minimizes the risk of vulnerabilities right from the start. Regularly applying security patches and updates to both runtimes and libraries is essential for maintaining security over time. Operating with the principle of least privilege means restricting permissions and access to programming language installations and resources, which helps limit potential exposure. Finally, enabling comprehensive logging and auditing is a critical practice. It allows you to detect and investigate any security incidents that may occur, providing you with insights necessary for response and prevention. In this section, we focus on secure coding practices tailored to specific programming languages. Each language comes with its own set of vulnerabilities and best practices to mitigate them. For C and C++, it is vital to manage memory properly, handle string inputs carefully, and use libraries that prioritize security. For Java, taking advantage of built-in features like the Security Manager, alongside validating inputs and handling exceptions appropriately, is key. In Python, the emphasis is on input validation, secure treatment of file operations, and ensuring the integrity and security of third-party libraries. Finally, with JavaScript, it's essential to sanitize user inputs, implement secure authentication and authorization mechanisms, and keep all libraries up to date to protect against common vulnerabilities. Adhering to these practices significantly enhances the security posture of applications written in these languages. When integrating security into the software development lifecycle, each phase must address specific security considerations. During the requirements phase, it's essential to define both security and privacy requirements. This involves threat modeling and adhering to secure design principles. As the design phase progresses, security controls should be incorporated, and an emphasis should be placed on developing secure architecture patterns alongside proper coding guidelines. In the implementation phase, applying secure coding practices and utilizing security-focused libraries is vital, as is conducting thorough code reviews to catch any potential vulnerabilities early. Testing should include a comprehensive range of security testing methods, including vulnerability scanning and penetration testing, to ensure the robustness of the software. Finally, during deployment, it's important to secure configurations by applying necessary security updates and enabling logging and monitoring to track and respond to potential security incidents effectively. In this slide, we're concentrating on monitoring and incident response for programming language security. Security monitoring involves continuously observing deployments to identify vulnerabilities, misconfigurations, and any suspicious activities. This ongoing vigilance is essential to protect and maintain the integrity of software systems. For incident response, it's critical to establish structured procedures that allow for the swift detection, investigation, and resolution of security incidents. Being prepared to act quickly can significantly mitigate the impact of any security breach. When it comes to vulnerability management, the focus is on being proactive. This means identifying, prioritizing, and addressing vulnerabilities in programming language runtimes and libraries before they can be exploited. Finally, compliance and auditing ensure that deployments adhere to both regulatory and organizational security requirements. By meeting these standards, organizations can maintain trust and confidence in their software systems. In wrapping up our discussion on monitoring and incident response for programming language security, let's focus on the conclusion and the key takeaways. First, it's important to consider secure language selection. Evaluate the security features and controls of programming languages to ensure they align with your security needs. Next, implementing secure coding practices is essential to developing applications that resist common vulnerabilities. It's also crucial to ensure that your programming languages are deployed securely and that there's ongoing monitoring for any incidents. Finally, integrating security into your software development lifecycle is vital to reducing risks and strengthening overall resilience. These core elements form a solid foundation for maintaining secure applications.